All right, we are live now for the new meetup organized by ContinualAI, the May meetup. After a long series, I would say, of meetups we have had, and we are actually uploading on YouTube. So feel free to see those if you want to learn more about this topic and learn from awesome speakers like the one we are now having today, like George, Lorenzo, Leonardo. So let's take a look of the actual schedule for today. Let me share my screen real quick. Okay, and you should be able to see my screen. Here I have the schedule for the May online meetup. That is going to be all about continual learning at the edge, on-device training without forgetting. So we're going to start with Leonardo Ravaglia from the University of Bologna. He's going to talk about memory, latency, accuracy trade-offs for continual learning on a RISC-V extreme edge node. Then we're going to hear from Giorgos Demosthenous from the CYENS Center of Excellence, and talking about continual learning on the edge with TensorFlow Lite. And then we will hear again from Lorenzo Pellegrini from the University of Bologna about continual learning at the edge, real-time training on smartphone devices. So I guess it's going to be like a very interesting lineup of talks. I think these are like the few papers out there that are actually doing continual learning on edge devices, on embedded devices with limited computational and memory resources. So it's really interesting to see that we're finally reaching a point in which we start really deploying these algorithms at the edge. And so I hope this discussion may trigger even more relevant and more interesting future works in this area, which I think is very interesting and relevant for the future of pervasive AI systems in general. So without further ado, I would now hear the talk from Leonardo. So Leonardo, please set up your, let me see if I can get back here. Well, okay.
Can you see it? Can you see the presentation?
Yes.
Yes, we can see it.
Great.
Okay.
So thank you, Leonardo, and please go ahead with your presentation.
Okay. Thank you for the introduction. So as you said, we're going to talk about memory latency accuracy trade-offs for continual learning on RISC-V extreme edge node, which was presented at SIPS in 2020. And our work is instead in the context of tiny machine learning. Tiny machine learning merges two major trends that are visible nowadays. The growing presence of IoT sensors, which will grow further also in the next years, and the major trend of AI and machine learning that developed in the last few years. And so we can think to many applications by merging these two, let's say, lines of research. And for example, for applications of pharma automation, for the production of smart sensors, and also for wearable technologies. For example, as for hand gesture recognition, if we consider to put the devices into the sleeves of clothes. But applications are virtually limited, and so we can think to many of them. But the kind of devices that we target in this paper, and in particular, which are very well suitable for IoT applications, are microcontrollers. Even though there are hundreds of devices which are characterized basically by their power consumption and by the amount of gig operations that they can perform per second. As we can see from this plot, not all the devices can perform training of machine learning models. This is in particular due to the fact that training is very resource required in terms of memory and energy. And the kind of, let's say, the portion of these plots that we focus on is the class of devices that consume about 0.1 watts. So very, let's say, restricted power consumption. But we demonstrate that they can perform machine learning tasks at the edge, in particular, also to perform a kind of training. But what previous to this work used to happen is that, let's say, the training of the models is uploaded to the cloud, to cloud servers. But this has several issues, for example, concerning the privacy and the latency and the scalability of the models, but also it will lead in the very next years to an increase in power consumption due to the transmission of data, since we will have billions of devices. And so it would be beneficial, at least, to keep the most of the computation possible local to the device, also preserving privacy. And so the contribution of this seminal work that we did is that we evaluated the memory and computational requirements of an algorithm of continual learning, specifically continual learning with latent replace. And we proposed a PULP-based hardware software architecture, where PULP stands for parallel ultra low power, that I will introduce in a few moments, tailored for continual learning. And we will benchmark the continual learning computational flows on the PULP device. To briefly introduce what is continual learning with the latent replace, we took the algorithm developed by Pellegrini, Graffietti, Lomonaco, and Montoni in the paper Latent Replay for Real-Time Continual Learning, and which basically works as follows. Images are forwarded through the network, and let's say activations, which are the orange cubes, are stored apart in a latent replay memory, so that they will be later used during the continual learning events in order to retrain the end portion of the network, and in order to reduce the catastrophic forgetting issue, which is well known to the continual learning community. And the model they adopt is a MobileNet V1 with a final classifier which has just 50 outputs. And the device that we target, as I said, is inspired by the PULP project, which stands for Parallel Ultra Low Power, which is a completely open source project developed jointly by the University of Bologna and ETH in Zurich. And it is a state-of-the-art microcontroller system with a multi-core platform, which allows to perform also, let's say, computation-intensive tasks like deep learning, inference, or even training of the models, with a peak power consumption tested on the hardware as little as 50, 60 milliamps. Let's say the main characteristic that we focused on in order to assess the feasibility of continual learning on this kind of devices was the sizing of the memories. And we considered an L2 memory of up to 1 megabyte. And accordingly to the, say, PULP platform, we have on the MCU side of the device a single core, RISC-V core named the cyber controller, while on the cluster side, which is called the cluster, we will have an L1 memory, which is tightly coupled with 8 cores. The L1 memory will have up to 256 kilobytes. And yes, these are the RISC-V cores, each with a private floating point unit. So to perform, say, operations in floating point with floating point 32 bits data. Okay, so we assessed initially the memory requirements of continual learning with latent replace, and we observed that keeping the accumulation layer closer to the end of the network, so to, let's say, to the loss side of the network, the memory requirements of to store the latent replace and also to retrain the network, the end portion of the network, will be, let's say, less than 16 megabytes. But the memory requirements will grow as we move the accumulation layer to previous layers, since the tensor of activations that we have to store are larger, but also we will have more parameters to train, and so more gradients to store. And to measure and to understand the computational flows of continual learning, they are basically equal to a generic deep learning algorithm, since the main operations that are performed are the forward of the images and also the backward propagation of the error and the computation of the gradients. So how does it work? Basically, we're storing the external large memories, which have space up to 64 megabytes, all the frozen parameters of the network, and all the, say, latent replays, which are then moved through the micro DMA to the L2 memory, and then through a mechanism called double buffering, they are moved to the L1 memory in order to be dispatched to the 8 cores in a way that the cores and the cluster never stops computing, since the transfer of data and the time of computations are balanced. These are the performances that we achieved, expressed in meg per cycle, which means multiply accumulations per clock cycle. And we see that the parallelization is well exploited, since the speed ups of the 1 core versus 8 core implementation is of about 8. So we are exploiting fully the 8 cores of the architecture. And yeah, in order to determine the overall latency of the continual learning flow, we estimated the amount of MAC multiply accumulations that will be performed in order to do continual learning, and we express the latency depending on the layer of accumulation that we are considering. So if we just retrain the final fully connected layer, the latency will be in the order of 1 second, but it will grow up to 5 hours if we consider to retrain the full image, the full network by storing plain images. And by training, I mean learning a single batch of images, which represent just one class of objects. So we should find a trade-off between huge span of latencies, depending on the application that we want to implement. And so to conclude, we assess the memory and computational requirements for a rehearsal-based continual learning algorithm, latent replace. And we also estimated in the paper to be 11 times more energy efficient with respect to the mobile class solution, mobile-based solution presented in the paper using a Snapdragon 845. So in the future works and in the current works, we worked in order to compress and quantize the data of the network and the continual learning flow, so to reduce memory requirements up to 4 times. And what we want to work on next is the implementation of a new application adopting the training lib that we developed for PULP devices, and also to automate and optimize the continual learning flows just for the PULP platform. So we are fully open to cooperation for this kind of task. And you can see an application use case, which is the nano drones, in which we may think to apply also continual learning, for example, for extending the ability of the drone to detect new obstacles over time. And so that's all for this presentation.
Thank you so much, Leonardo. I think it's very nice to see how continual learning can be applied not only to, I mean, what we would consider like edge devices already constrained in terms of memory and computation, like mobile phones, but can go even, beyond that on wearable devices and things that like can run on batteries, essentially, right? And maybe since many of us here, I guess, are not familiar with that particular world of devices. So maybe can you clarify or recap essentially what's the, let's say, the I don't know, average battery duration for this kind of device? And I mean, how continual learning could really work in these settings? I mean, you mentioned that, for example, in that strategy where you decide the kind of let's say, latent replay layer, then that impacts, of course, the training time needed on this particular very low computational platform to update the model based on just a single new batch of data. And so, I mean, how long would the battery, for example, last for these devices? It is reasonable to do so. So to update maybe the knowledge about a particular object. And I mean, what are your thoughts on these? Just a simple like object recognizer would be possible already on these, for example, wearable devices.
Yeah, what we estimated is that, for example, to perform retraining every minute or every hour, depending on the needs, of course, will change a lot, of course, the duration of the device. But we can imagine just by doing one retraining per hour to achieve, I think, about 300 to 400 hours of life duration for the device. Since when the device do not perform the training, it is basically all switched off. Also, the class is switched off, so the power consumption is very, very. Yeah, it very much depends. If we imagine, for example, that we want to detect the new face of a person that is pictured, we can imagine doing this task every once in a year, for example, when we want to teach our system to recognize just a new member of the family, for example, or a new guest to a bed and breakfast. And so,
nice. It's very nice, and how you can proceed. I mean, with your work on these, and and maybe apply it. It would be fun to apply it on the mobile drones that you showed. I think that's very cool. So we look forward to
that.
Great. We look forward to a demo about that. Do we have like quick questions? Maybe a quick question to Leonardo from the audience. Maybe you want to just open your mic and speak up, or send your message on the chat. Otherwise, I think we can move on, and we will answer to these questions directly later during the panel session. So I don't see anyone here with the raise hands or anything appearing on the chat. So I guess we can move on, and we can now let George speak about his very recent work. I was very impressed. I mean, to see something really working out of TensorFlow Lite, right? Because I think that's the let's say toolkit that was used for this paper. So I'm really keen to hear from George about his experience about this, and I mean that's very nice because it's. I mean we worked, and Lorenzo, we will talk about that later a lot, on trying to understand what were the actual frameworks available to do this instead of just writing everything from scratch, right, in C++. But now it seems that there are progresses finally in this sense, and so I'm very happy to hear that TensorFlow Lite is essentially stepping up in this, at least. So thanks, George, for your time, your presentation. I'm very happy to hear what you think. And please go ahead with your slides. You're sharing your slides, and presenting your work on TensorFlow Lite.
Can you see my slides?
Yes, we can.
Okay, so hello everyone. Thank you for inviting us to this meetup. My name is Giorgos, and I am a research associate at the Learning Agents and Robots MRG at CYENS. Today, I'm going to present to you the continual learning on the edge with TensorFlow Lite. But before I do that, let me very briefly introduce who we are and what we do. CYENS is a research and innovation center on interactive media, smart systems, and emerging technologies. It is supported by the European Commission and received funding from the EU's Horizon 2020 program. Members of the project include the Municipality of Nicosia, the Max Planck Institute for Informatics, University College London, University of Cyprus, and others. Research at CYENS stems from three research pillars: the visual sciences, human factors and design, and communications and artificial intelligence. The research focus of our MRG is on reinforcement and deep learning, multi-agent systems and computational intelligence methods for creating autonomous software and robotic agents that learn to solve and adapt to dynamic environments. Vasilis is a team leader and is also the co-author of the paper we are about to present. So very briefly, in recent years, there has been a rising trend of taking deep learning models out of the lab and deploying them on the edge, like robotics, smartphones, and other embedded devices. This has also been an ongoing effort to discover real-world and everyday usage for mainstream adoption of this technology. So most appropriate approaches today focus on training their machine learning models offline and deploying them on the edge only for inference. Although this approach is good enough for certain applications, many times it is desirable to allow on-device training of the models as well. So such cases might be where there are some privacy limitations, some network issues, or even some scenarios where we require personalization and fast adaptation. So Google, who backs the development of TensorFlow, has picked up on this growing need and is now working on embedding on-device training functionality to their TensorFlow Lite library. Their current experimental approach focuses on using transfer learning for on-device personalization. So transfer learning has been shown to perform extremely well when faced with learning new classes fast by training only on a few samples. And although transfer learning is a good first step for on-device training, it has some issues. For example, in order for transfer learning to work, all new classes must be present at the training batch while learning. Otherwise, the model will suffer from catastrophic forgetting when new classes appear incrementally over time. Unfortunately, in most real-world scenarios, new classes do appear incrementally, which makes transfer learning unfit for many specialized applications on embedded devices. So the solution is a continual learning approach. For this reason, in our work, we expand the current experimental TensorFlow Lite library to include continual learning capabilities. First of all, let me just say that the reason we chose to expand TensorFlow Lite is that their models and overall library is optimized for running on embedded devices. Therefore, it is a much better approach rather than hard-coding the entire functionality ourselves and then compiling it to run it on an embedded device. So having said that, what we did is built on top of a transfer learning model. Specifically, the model is separated into two parts, known as the base and head. The base of the model is a mobile net and was pre-trained on an ImageNet dataset, and the head of the network uses the features extracted from the base to learn new classes in real time using only a very limited amount of data. And this flexibility allows us to experiment with several continual learning capabilities and limitations directly on the device. So what we did was to implement a simple naive rehearsal approach into the network. Specifically, we added a replay buffer at the head, where instead of storing entire image samples, we stored feature patterns extracted by the base model. This way, our deployed model uses a lot less resources when replaying and storing the samples. More information about that can be found in our paper. So before deploying the model, we first needed to measure how it performs in a continual learning setting and compare it to transfer learning. So For this reason, we use Core E50 dataset and specifically the new instances and classes benchmark scenario. Here, the new classes and instances of classes are presented to the model incrementally over time, and the accuracy of the model is evaluated after each training batch to examine its ability to continually learn. So as you can see from the graph, transfer learning fails dramatically in this continual learning scenario, whereas our continual learning model is successful in learning incrementally over time. So we also compared our model to the AR1 star with latent replay algorithm, which is a state-of-the-art continual learning algorithm that combines some architectural regularization and memory approaches to allow the entire network to continually learn. We use this algorithm as an upper bound to our model because when we lower its latent replay buffer to the lowest possible layer of the mobile net, makes it comparable to our own model. And as you can see in the table, we achieve an accuracy close to that of AR1 star, which means our model performs well enough and is ready to be deployed on an embedded device. So we deployed both continual learning and transfer learning models on an embedded device in order to compare their performance in real-world scenarios. So we expanded the TensorFlow Lite experimental API and application to create our own demo application with both continual and transfer learning functionality, which then we deployed on a Samsung Galaxy S10 Android smartphone. This allowed us to train and test both models on the device and compare their performance for a variety of scenarios. And the APK and source code of the Android application are both available on our GitHub page. So we experimented with 3 different scenarios. The entire training and evaluation procedure for each scenario can be seen in our demonstration video, which is referenced in the paper and available on our YouTube channel. So the first scenario is a cumulative scenario. Here we add 50 samples from each of the 4 available classes seen in the first instance row of this figure. We then use all 200 samples to train both models at the same time before evaluating their performance. In this scenario, 0 samples are replayed to the continual learning model. For the second scenario, the new instance scenario, just like with the cumulative one, we add the 50 samples per class from the first instance row and train both models using all 200 samples at the same time. The replay buffer is then populated by 10 random samples from each class, and we then introduce new instances to the same 4 classes as seen in the second instance row of the table. After adding the 20 new instances per class, using the new instances, we train both models with all 80 new samples, and we then replay 40 samples from the buffer to the continual learning model. The new classes scenario is the most important one because it mostly closely resembles a natural setting when the model is deployed on a continual learning device scenario on an embedded device. In this case, we incrementally introduce new classes to the model. In contrast with the previous scenarios, we add 50 samples for a class and train both models before moving to the next class. And every time a new class is introduced, all samples that are already in the buffer are replayed to the continual learning model, and 10 random samples for the new class are added to the replay buffer afterwards. We repeat until both models have incrementally trained on all 4 classes. Now let's see the results of each scenario. For the cumulative scenario, since all the data is available during training, both models have no issue learning and classifying new classes with perfect scores. The orange rectangle, as you can see in the picture, denotes which class is selected during inference, and the confidence score is visible below the current class. In the case of the new instances scenario, we can see that the continual learning model has no issue whatsoever in classifying correctly and with perfect scores all the available objects. Transfer learning, on the other hand, despite having all new instance data available during training, is already showing some evidence of forgetting with slightly reduced confidence scores. And although the effect of introducing only one new instance is minimal in this case, We expect that the transfer learning model's performance will continue to decay as new instances are introduced in the future. The real strength and usefulness of the continual learning model over the transfer learning one can be seen clearly from the new classes scenario. In this scenario, the continual learning model correctly classifies all 4 classes and with near perfect scores. The transfer learning model, however, fails dramatically and is able to correctly classify only one of the 4 classes. Specifically, it only correctly classifies the notebook class, which is the last one introduced during the incremental training. This is clear evidence of catastrophic forgetting when the model is trained using transfer learning in a more realistic classical data scenario on the smartphone device. So we have kind of proved the usefulness of continual learning on embedded devices and its superiority over transfer learning. The next step is to examine the robustness of the continual learning model under non-ideal conditions. For this reason, we trained and test the model on 4 new classes, and in contrast to the previous experiments, we now collect 70 unique samples for each class with varying characteristics of difficulty. A sample might have a different orientation or depth. The background and light conditions are constantly changing. The object in the image might be cropped or blurry, and some unique characteristics of the object might be hidden. Again, the entire demonstration video is available in our paper and our YouTube channel. So when testing under such realistic conditions, the continual learning model still manages to correctly classify the objects in the camera feed most of the time with high confidence scores. And despite its generally good performance, the continual learning model still fails to correctly classify some of the objects in some specific situations. So we identified 3 main situations. For example, when we have the remote control of the television rotated so as to hide all the buttons, the model fails. So here we have a key characteristic that is hidden. Another example is when the handle of the cup is not visible, so it is cropped or blurry. And a third case where it fails is where the bottom of the water bottle is shown and the cap of the bottle is hidden. So again, when a key characteristic is hidden, the model seems to fail. So to conclude, in this paper, we have shown that the current TensorFlow Lite experimental transfer learning implementation is incapable of handling realistic continual learning tasks simulated through the Core E15 benchmark and demonstrated through our own Android application. To solve this issue, we expanded Google's TensorFlow Lite library to include continual learning capabilities by introducing a simple replay buffer into the current transfer learning model. The code for our demo application will be open source to enable developers to integrate at the moment continual learning to their smartphone applications, as well as to facilitate further development of continual learning functionality within the environment of TensorFlow Lite. In the future, we will focus on implementing additional continual learning methodologies like regularization, modularity, and more sophisticated rehearsal techniques within, again, the limitations of TensorFlow Lite by altering, for example, the head of the model and increasing the overall complexity. So yeah, thank you, and feel free to ask any questions.
Thank you, Georg. I think now I nailed better the pronunciation. Sorry about the before. But yes, I wanted to ask you a quick question about the support that TensorFlow Lite is providing. So essentially, you said that you're using TensorFlow Lite because it's efficient in inference, especially, I guess. And then they also provide like this new, let's say, module that you can use to define your own, let's say, ad of the model and customize it and train directly on the device. Is that correct? First of all, yeah. Okay. Yeah. And does this new module, which I think it's separated from the main TensorFlow Lite code base, does provide support for defining any, let's say, computational graph, or it's just limited to fully connected layers, I don't know, and just a few operations?
No, it does not offer the full support. That's why it is completely separated from the main TensorFlow Lite library. But they have a variety of operations that they do offer, and they do not offer all the graph complexity. But there are still a few things that you can do in the head, and they are currently working on expanding all the operations that you can do in compile there.
Yeah, because I don't really get what they are doing. I mean, I guess that it's tough to bring the whole TensorFlow Lite dependencies and code base to let's say, edge devices. But at the same time, if they plan to actually make TensorFlow work also you know, on these kind of devices for training later on, I don't really understand why they're like developing like a separate code base for this. So, but I guess I should ask them. Yeah, so thanks, Georg, for your presentation. It was very nice to see that new groups are working on trying to bring continual learning strategies to the edge, like on smartphone devices especially. I think that this is going to be a very interesting line of work. Especially on Android phones, but well, any OS. But I guess, I mean, trying to make machine learning in general, even not necessarily like continual learning, but machine learning training on device may be like a very interesting and futuristic, let's say, field of research that would enable pervasive AI application to actually run on a device that we all possess, right? So that's really nice. Do we have any more questions from Georg before moving to the last presentation of the day? Please raise your hand or just write your question in the chat. Unfortunately, I won't be able to stay much longer. So I will let Andrea Cossu, who is here, take the reins and later on moderate the panel discussion. But so please stay connected after the Lorenzo's talk to be sure to attend these very nice discussions we're gonna have with a few interesting questions, like for example the choice of the specific libraries maybe for your own experiments on training on device, how we can phase maybe European regulations for training and using data, and preserve maybe robustness and security of our AI systems, and all these interesting related questions that I think it's worth discussing with you all. So thanks, Georg, again. Please, Lorenzo, go ahead with your presentation, your slides.
Nice. Can you hear me?
Yes, we can.
Okay, perfect. Okay, I'll just share my screen. Okay. Hello, everyone. Well, my name is Lorenzo Pellegrini, and I'm a PhD student at the University of Bologna. Today, I'll show you the Continual Object Recognition Android application, which is an application which has been around for a while. We finally completed some experiments and more, let's say, proper tests on this application I want to show you today. So I'm, apart from being a PhD student at the University of Bologna, I'm also the lead maintainer of the Avalanche benchmarks module. If you want to take a look at the Avalanche, it's a very nice framework for continual learning, but let's talk about the application now. So the goal was to demonstrate the potential of continual learning to tackle a realistic problem in a realistic environment with a minimal user interaction schema. We wanted to tackle a situation, a scenario, which is the new instances and classes, a task-free scenario in which you encounter both instances of new and previously seen classes during time. And the application was targeted at consumer devices with no cloud involved and no particular accelerators, so very plain consumer devices. We wanted to keep the training time very limited with a very limited memory usage too. And the idea was to create a privacy-friendly application, and we see how this is achieved. So the context for this application is the Continual Object Recognition 50 video benchmark. The idea is to target a use case which is similar to the data seen in that benchmark, which is a very, let's say, popular benchmark as of now. It contains a video session, 11 video sessions of 50 different objects grouped in 10 different categories. I think you already know about Core 50, so I'll go very quick in this. Those are images taken from the Core 50 videos showing the 50 objects contained in the dataset. As you can see, it's an egocentric point of view, which is the same point of view that we wanted to target with the continual object recognition application. So very briefly, I think it's better if I just show you the trailer for the application. I will. It's on YouTube. You will find the link in the slides. I'll post later on the Avalanche forum. And this brief video shows how the application manages the the three main functionalities: inference mode, which is the one you are currently seeing, and the application is pre-trained with the Core 50 categories. So we are classifying at the category granularity, not at the object granularity. And in inference mode, it just outputs the confidence score for each category. And you can improve the, as you can see here, the recognition capability for an existing category by just taking a very short video of 100 frames of a new object of an existing category. You just have to tap on the thumbnail and then the process starts. As you can see here, the application was able to recognize the new object, this plug adapter, black plug adapter that was not recognized before. And you can also add new categories. You have these 5 empty slots here, just below the 10 initial ones. And for instance, here we are, let's say, learning how to recognize the stapler, which was not in the Core 50 categories. And as you see, it works quite well. And it can also sometimes manage to generalize on the objects of different shapes, slightly different shapes and colors, while keeping good performance on existing categories. Again, if you want to take a look at the video, there is a link in the slides. And you can also have a look at the archive paper that has been published just today. And you can also install the APK alpha version of the Android APK you can find on GitHub. The source code is not public yet, will be available in the very near future. So let's talk about some technical details. The application is slightly different from the one showed by Georgi because it packages the whole Caffe framework inside the application, as well as an implementation of the continual learning algorithm, which is the AR1 star with latent replay algorithm inside of it. We use a mobile network version 1 trained on the Core 50 categories. We keep everything in 32-bit floating point, mostly due to technical limitations of the Caffe framework. And we use a very small buffer of 500 instances. And speaking about replay, the replay here is incredibly important to prevent a complete forgetting, especially considering that we are training with videos depicting a single object and where frames of the same video are very, very correlated due to let's say, correlations of each frame. So we would get an extreme forgetting if we didn't use a replay buffer. Here, a replay is absolutely important. There are few issues about replay, especially the performance of replay, which makes training times explode, but it also takes a lot of memory to store a lot of patterns for replay. And of course, there are privacy issues going on when you store whole images, the original instances. So the idea was to use a latent replay mechanism which stores the activation at a certain latent replay layer, an intermediate layer inside the network, to store those activations instead of the original data. And the idea is, well, very simple. You keep the part before the latent replay layer frozen or very slowly moving, training, and the part just next the latent replay layer, you just train it using SGD or some kind of other, let's say, optimizer. And we selected the penultimate layer of the network for this latent replay layer. That is, we just keep everything frozen before the last fully connected layer, which makes for a 500 replay buffer. The 500 replay buffer actually takes less than 2 megabytes, because for a mobile network version 1, we have just to store 4 kilobytes of data for each element, for each replay pattern. And then we apply copy weights and reinitialize at the last fully connected layer of the model to further reduce forgetting, which is a very light approach, a bias normalization approach that has nearly no impact on the training time. So the application has been around for a while, but no proper experiments were made on the application, on the algorithm used in the application. As I told you before, we are acquiring one single video of possibly or new or old categories of objects, and this is the use case covered by the NIC 391 benchmark, which is based on Core 50 dataset, in which we have experiences made of one single video depicting one single object. And we don't know if in the next video session we'll encounter a new or already seen category. And the good part of this is that we can generate multiple runs by inserting new classes of objects during time in different moments. And we can also, let's say, shuffle how which video session are encountered over time. So it's a very good benchmark. The problem is that the Core 50 dataset was already used for pre-training and filling the first 10 default categories of the applications. So the basic idea is to gather a similar dataset and test on it. So instead of using Core 50 dataset for the experiments, we still use it for the pre-training phase, for pre-training our model, but we then gather a new extended version of Core, which is made of 25 objects of 5 new disjoint categories, which are not found in the Core 50 dataset. It's very similar. It contains 12 with the sessions for each object, so one more session for each object than Core 50, but differently than Core 50, we captured it using smartphone devices instead of the Kinect used for the Core 50 dataset. So we have more variability with respect to brightness, especially image quality and stability. The images are kind of worse with respect to the Core 50 dataset. So it's more akin to the use case, to the situation you'll find when using where you'll be using the application. Just to show you which are the contents of the dataset, you can have a look at the image here on the right, and you can see that the brightness and image quality are very variable. They change a lot depending on various factors. They use the smartphone, the brightness, if it's indoor or outdoor, if there are clouds or not. So it's very realistic, we are in a very realistic situation. And just to show you how a typical the benchmark used for our experiments looks like, we use the benchmark generation procedure from the Core 50 NIC 391, but instead of using Core, we use that extended dataset, obtaining a training sequence of 225 incremental experiences, each experience containing a single video of our object. And we compared with three different categories: unbalanced replay, class balanced, and AR1 with latent replay, which is the one we actually implemented inside the application. We want to check if the application can learn new categories of objects, those 5 new categories, without forgetting the ones from the pre-training phase from the Core 50 dataset. And we start with a replay buffer, which is a fixed size, 500 instances, and balancedly filled with with some patterns, some instances from the Core 50 dataset. And for each strategy, we tested both its frozen version and unfrozen version. This freezing below the last fully connected layer, or by keeping everything unconstrained. For AR1, this means having a latent replay layer just before the last fully connected, or replaying from the input, non-latent replay. But we also test, in addition, replaying at the convolution 5.4 layer of the MobileNet 1, which offers a good trade-off between accuracy and training times. So those are the results. I will go very fast here because those are in the papers. We'll discuss the papers, and especially training times. We finally have we standardize our testing, let's say, methods. The implementation of AR1 with latent replay executed at the last fully connected layer is very, very fast. The training phase that follows the image gathering phase takes less than 200 milliseconds. So those values here are in seconds. Retraining from input takes, well, a lot of time. And we have a decent trade-off while using an intermediate latent replay layer put at the convolution 5.4 layer. The good thing about using latent replay is that we can run a feature extraction, the feature extraction procedure where we extract the activation at the latent replay layer during the gathering phase. So while we gather images, we are actually running a forward pass with those new images and storing those activations for future use for during the training phase, which makes the training phase very, very short, again, less than 200 milliseconds, so saving us about 9 seconds of time, making the app very, very responsive, very, very to update the internal model. Unbalanced replay can prevent forgetting, which may be related to the fact we are using a very small replay buffer, but again, unbalanced replay just replaces a fixed amount of patterns after each experience. So previous patterns from the Core 50 dataset will get probably quickly out of the buffer. Balanced replay, class balanced replay is good, but the frozen variant is good at define forgetting on new categories and not so good at learning new categories. And while keeping everything not frozen, the input variant does exactly the opposite. So it is good at learning new categories, but bad at keeping the informations about the previous ones. While AR1 with latent replay at that intermediate layer convolution 5.4 is the best accuracy trade-off you could find. In the application, we wanted everything to be really, really fast, so we used the frozen version of the AR1, but we also suggest that using a delayed sleep phase could be great. For instance, using the convolution 5.4 variant, because it's very keen to how biological systems works, how they consolidate knowledge, and will allow for better accuracies, but it takes a few minutes to complete, so we have to delay it in a sleep phase. This may be a good idea. It's not already implemented in the application, but is a good, maybe a good solution. So a two-step consolidation, fast one plus a slower one delayed. And in conclusion, I think that we are moving very, very fast toward personalized and privacy-oriented continual learning experiences for user devices. And there are a few problems here that have to be solved. From a research perspective, we have very slow adoption of realistic benchmarks, and new classes, which are, let's say, task incremental, class incremental benchmarks are not always really realistic in some real use cases. We have few very scalable strategies that can be adapted depending on the desired accuracy performance trade-off. And the huge problem here is about frameworks is, well, as Georgos said before, you have to implement something atop of an existing deep learning framework. We here compiled Caffe from scratch, so we had a fully working deep learning framework. But if you want to use mainstream framework, which are more optimized for mobile and even support quantization or things like that, you have to implement your training procedural training algorithm, including backward propagation and stochastic gradient descent, probably in a separate way. And I would like to see more support from mainstream frameworks for training on device. And of course, if we want to tackle more vision tasks for realistic physical objects, we need more video datasets instead of ImageNet, which has one image for each object of a certain usually grain, not fine grain category. We need more video datasets depicting single objects. And I think in the future that continual learning may be really good also for non-user-centric application, which are however still privacy related, like industry related, or for IoT application and things like that. This concludes my presentation. If you want, there is the fresh paper we just published on arXiv. You can have a look at how we, let's say, think about this AR1 algorithm in a previous paper that was accepted at IROS. And you can also download the application. You will find all those links right in the last part of the slides. I will push to the Continual AI forum very, very soon. Thank you.
Thank you very much, Lorenzo, for your great presentation, as usual, of course. So please join me in thanking all our speakers today, because they did a great job, and I think we are seeing the most up-to-date application, bleeding edge application of continual learning. So, I mean, it's something for the field, right? Also because we need these applications to start looking at continual learning also from a practical perspective, and to start gathering together people interested in continual learning. So I'm really happy to see this finally happening in our field. So of course, if you have any questions for Lorenzo, or to direct it to him or to the other speakers, feel free to raise your hands. I think you have many options. You can raise your hand, you can write in the chat, you can unmute yourself, and feel free to speak up. Otherwise, I think we can start with a round of questions and answers, hopefully. And I think that the main point touched by all the speakers is the framework, right? So from TensorFlow Lite to Caffe, C++, I think there are lots of things here. It's not simply like training a model and then in some easy way deploying it in the edge. So I would like if the speakers can share with us their experience in these terms. So what is, in your opinion, the main difficulty in deploying a machine learning? So if I want to deploy, I have my model and I want to deploy it on, let's say, on a smartphone. What is the first thing that I should learn, for example? Is the right framework, or how to make my model small? I mean, if you have some practical advice to deploy your continual learning model, and if you think that the framework will adapt, so will satisfy our requests when we produce many applications, or instead if we need the framework to come first, right? So to enable, to ease the process. I think, yes, we can start with this, if any of you has any opinion on this matter?
I mean, I think in terms of whether we should wait for the frameworks to evolve or not, I'm not sure we should wait, because we shouldn't act retroactively. And although you might, let's say you want to start now and deploy your application on the smartphone, in case you do not need fast online training, most of us will go with using a server and an API. But as we see more and more limitations rising now, especially with issues like GDPR and health privacy that needs to be within the smartphone, we cannot wait for the frameworks to be deployed. We need to sort of push the industry ourselves, and this way the big frameworks take notice and start developing the code themselves. Such is the case with TensorFlow, right? Because I was researching and I found out that they are actually looking to developing a full training framework for the phone, but mostly they are limited due to the limitations of the devices generally used by the population, because some might have high-end devices, but the majority of the population still cannot run such models on their device. So the battery runs out very fast, the phone might overheat. So for now, they are just experimenting with simple personalization models.
Yeah, great. So, I mean, this answer also supports the fact that we should thank you for starting this journey, because I think it's quite difficult to start when there are no tools basically around. So I don't know if Lorenzo has something to say about Café, because I'm very curious about how to integrate in Café. And well,
yeah,
if you would start your PhD right now, would you do the same? And provided that there is no alternatives, but would you embark yourself in this journey again?
Oh, well, I started my PhD where we actually had continual learning code base only written in only Café. So there was no code for TensorFlow and PyTorch. I now switched to PyTorch, and yeah, we shouldn't look back. I mean, Café was great, and the good thing that with very few adjustments, you can compile it for Android and probably also for iOS and things like that. But it's a very legacy framework and is difficult to use, especially when using the C++ API. So it was very difficult. It's very difficult to use, to compile, to port. Is okay. It's we shouldn't look back. I recently had the chance to use TensorFlow Lite for, well, not continual learning tasks, and is very great in dealing with inference on devices. Is really fast. Is very easy to make your model integer 8, let's say, to quantize your model. So we definitely should try to use newer frameworks. The problem is that Café offered the most freedom for us. For instance, running a latent replay from a different layer from the last one. So an intermediate layer, it's hard to do if you don't have a proper implementation of forward, backward operations, optimizers, which you don't have currently for TensorFlow Lite. So you have a very minimal implementation for fully connected layers atop of TensorFlow Lite, but we absolutely need the new frameworks. And again, I agree with Georgi. We shouldn't wait for frameworks to come and offer their support for this kind of things. We should move first and then, let's say, get frameworks, let's say, to implement, push frameworks to implement the functionality we need. The problem is that by implementing things beforehand, before there is an actual official support from frameworks, is well, very time consuming, and that time spent implementing these kind of things may, well, get wasted in the same moment that the actual framework implements that functionality better in an integrated way. So you're probably writing a lot of code that will get, well, we have no use if you stick with this idea. However, this is the let's say, I think this is the way to go. So push framework producers like Facebook or Google or even Apple, I don't know, to offer training functionalities, better training functionalities, easier to use even from a, let's say, a Swift / Java / Kotlin instead of C++, directly on their inside their framework, because implementing it externally, I did it, is, well, it's really difficult. I don't recommend it. Absolutely.
Thank you very much for these precious insights on how things may work. So Leonardo, since there is also another thing I think is useful to know. So when you are thinking about deploying a model on device, what would you suggest to someone which is not experienced, let's say, in putting machine learning and continual learning now models in production? Do you have some, like, the major steps? Did you identify some major steps which one can use? And do you want to share with us, because it is not obvious?
Yeah, I think there is no secret. But yeah, for us, we basically started from scratch. Sorry, I have some background noise.
Yeah, no problem.
But we started from scratches, so we missed all the framework, basically, not only for continual learning, but also for training the networks. So we worked in order to develop just a tiny library, so to perform on the pulse device. But yeah, since the main loads of computations are let's say just forward and backward of the network, you just need to implement these kernels, and once you have these, let's say, you can easily estimate the latency, for example, for implementing it on the device, since they are the vast majority, in particular for mobile net, but I think for any CNN, the majority of time is spent on these matrix multiplications.
Yeah.
You have to think also to the tiling strategy in order to optimize the matrix multiplication.
Yeah, so I think that also the framework should focus more on these if they want to. Well, of course, if frameworks are driven by companies alone, of course they have to have a sense of advantage in building these tools. So for continual learning, of course. So I think there is a trade-off here between what we can expect from libraries and frameworks for cutting-edge research, which is always, I mean, it's research, so yeah, it's also normal that there is not much available because, I mean, we are exploring things. So yeah, I really hope, however, that this will change in the near future as more and more continual learning applications will emerge. And so yeah, I think that's the trend will be like iterating on this process. So people requesting features and frameworks adapting themselves and so on and so forth. When finally we will be able to scale and have a TensorFlow Lite perfectly working. Yeah, please, Georgi, you have something to say?
Yeah, I think I'm going to say something about the incentive. I do think companies, especially with the recent regulations from the they have to comply somehow. So as these regulations get stricter and stricter, both for the data as well as the AI, the frameworks cannot fall behind. So they have to evolve and actually offer this functionality to the developers themselves, not just the researchers, as to protect the developers protect their applications and their own audience from such issues that are currently being regulated and discussed.
Yeah, that's true. Yeah, I forgot to mention that point. You are completely right, because I mean, a company can have another incentive to build a tool, so to have obliged to do so, basically to be compliant with a regulation. And I think this is a very important point, as EU and US maybe are starting and will continue to push on this, on federated learning, which have some very tight requirements about this. So data transferability, all these points on privacy and so on and so forth will, in some sense, push continual learning to be developed, because in some way it may be needed. So there, for certain applications, maybe data sensitive applications will be needed. There will be no other solutions at the moment. So yeah, I think this is another important point. And of course, we as a research community, and I would say also as an association of continual learning, I think we have a lot to say about this. So it's not strange for science to interact with politicians and regulators. So I think we have also something to offer in this sense. But I mean, let's say, let's go back to continual learning for a moment. So I was wondering if during your research and your experiments, did you find the current set of available continual learning strategies enough for your work? So do you think that maybe the current continual learning strategies are not enough, maybe because are trained on, I mean, not only split MNIST, but just to give you the idea, so on synthetic or so on benchmarks, or maybe so they may scale up on more complex benchmarks, but we need to test them, or we need a completely different approach to invent new strategies that can work in these tight environments. What do you think? And also, of course, others, if you want to interact as well, again, please just unmute or raise your hand. I see Lorenzo's mouth moving, but
oh, okay, sorry.
Yeah, that's working.
A little technical problem. I'm kind of biased there because the Air One strategy was specifically made with this kind of ideas in mind. But there are not many strategies out there that can handle this kind of scenario. I mean, there are both research. Yeah, it's a research problem. I mean, we have a both problem with datasets and how datasets are used in continual learning to create that stream of experiences that those experiments we usually find in literature. So we usually find task/class incrementer, which is not particularly realistic, and we see it applied to Cypher10 or MNIST, which are absolutely not realistic. So we, apart from strategies, we absolutely first need data sets and new benchmarks. I mean, Core 50. With Core 50, we propose that long benchmark of 391 experiences. Hi Vincenzo. And
yeah, we have teletransportation here.
Exactly.
I forgot to mention.
And yeah, with that benchmark, we really wanted to create something, a continual learning benchmark which was realistic, but we can also find better ways to define benchmarks that are more, let's say, tied to a particular problem, real world problem, while current benchmarks are mostly virtual, not tied to a particular realistic use case. So this is my idea. We need benchmarks and data sets, absolutely.
Yeah, I completely agree.
Yeah, to that point, in terms of the realistic problems, I want to mention that we also need to define clearly what those problems are that continual learning is trying to solve, and then work backwards from there. Because in the more applied use case, when you're trying to build something, you're not sure whether you should use plain machine learning, federated learning, or something, or even transfer learning. And so it is another challenge to actually define clearly where continual learning is going to be used and work backwards from there.
Yeah, sure. There are any other observations from the public? No? Okay. So yeah, I mean, I have one last mention, but this is not a question because I don't know much about this topic. But it could be interesting also to look around for the trend of neuromorphic hardware, which is now in some sense growing. So these chips, which are made to run efficient kind of neural networks on them. So it would be great to see like a continual learning chip, so to solve many different problems, because we need to do training, so chips made for inferences and also frameworks made for inferences are not enough. So I think that there is a lot going on in this sense. So I'm very happy to see these works, and also to see, of course, Vincenzo's face now again. And so, okay, maybe we have okay, we have a question from the chat, so we know that the chat is working. Thanks, Antonio. Antonio asks, what are the properties missing from the current benchmarks to consider them more realistic? So I think this is a good question. So of course, apart from them being taken from the real world, I think that's of course the a definition. So MNIST is in some sense taken from the real world, but it is a, let's say, approximation. But do you need, what do you need to be contained in this benchmark to be realistic for and useful for this training? Can you identify some characteristics which are currently missing?
Oh, okay. I think that mainly, well, there are two parts of a recipe for a benchmark in continual learning. Well, this is what I think: the data set and how you actually use that data set to create experiences. So the first thing is to, let's say, have a data set which is akin, which is similar, has similar data distributions to the problem you're trying to solve. So it's very problem related. You want a realistic benchmark, you have to find a real problem and then get backward towards the benchmark. So you can start with a benchmark and fit it in the problem. You start from the problem, you get data for that particular problem or for a similar problem, and then you have to define how you split experiences, which is the huge problem here. Let's say new classes, let's say task/class incremental benchmarks are realistic or not. Well, depends. If you want to, let's say, only acquire knowledge for a certain bunch of classes, a bunch, then another bunch, then another bunch, yes, that would be realistic, benchmarks. But can you find an actual application that can, let's say, that has this kind of usage in the real world? Probably yes, but it's hard to find this kind of application. Again, I think that current benchmarks lacks a link to an actual real world problem, real world use case. So you have to start from the problem, come back, get a data set, and then you can try to define a benchmark based on how you think that system will be used. So I think it's that's it.
Yeah, I mean, that's true. And also in some way, I think that we still have as a community to address the continual learning, in the sense that we are not making assumptions on the stream of data we are receiving, right? So we, of course, models are focused on a specific task. So I mean, if it is object recognition, I will try object recognition datasets. but it would be cool and really great to see models also able to learn different tasks. But this is, I mean, akin of general intelligence, of course, which is quite far from now. But yeah, also the need to have benchmarks specific to an application is something that collides with the general idea of continual learning, which you have no idea what will be incoming. So it may be image, it may be sensors. You have to do this multimodal learning. So from that you can do whatever task you want, basically. But I mean, yes, for this, for the moment being, I think that also starting from this could be a useful approach in scaling up our applications. I don't know if this answers Antonio's questions, but in case, of course, feel free to let us know. So yeah, I mean, these are more or less the things that impressed me in these talks. Does someone has any other questions or wonderings of any kind? Okay, so I think that we can close this up. So thank you again to all the speakers for bringing to us these very nice applications. And well, stay tuned with Continual AI through our multiple channels on Twitter, LinkedIn, Slack, you name it. I think the next event will be on Friday, same hour, more or less, for the reading group of yet another great paper, of course. And yeah, see you soon. Bye.
Thank you,
Bye.
guys. Thank you all. Bye. It was nice.
Thank you for having us. Bye.
Bye.